Pluto, once considered a part of our planetary system, remains a fascinating and enigmatic object. Recently, astrophysicists Neil deGrasse Tyson and Michio Kaku have reignited interest in Pluto with their intriguing hypothesis that Pluto and Neptune could eventually cross paths. But how could this happen, and what might the consequences be for our solar system? Could this be a simple case of eccentric planetary motion, or is there more to the potential collision between these two distant worlds? Let's delve into the possible outcomes of a Pluto-Neptune encounter. Pluto, now classified as a dwarf planet, continues to captivate scientists with its unusual orbit. Its path around the Sun is far from ordinary, taking a lengthy 248 years to complete one orbit. Since its discovery in 1930, Pluto hasn't even finished one full revolution. What makes its orbit particularly interesting is its elliptical shape, which is markedly different from the nearly circular orbits of the main planets. Additionally, Pluto's orbit is tilted by 17 degrees relative to the ecliptic plane, resulting in a much steeper trajectory compared to the other planets. One of the most intriguing aspects of Pluto's orbit is its intersection with Neptune's orbit. For about 20 years in each of their orbits, Pluto actually comes closer to the Sun than Neptune, which seems counterintuitive given their positions in the solar system. This raises the question, why hasn't Pluto collided with Neptune? The answer lies in the gravitational interactions with other planets. Early studies of Pluto's orbit, conducted shortly after its discovery, revealed its strange path and the crossing of Neptune's orbit. Despite these complexities, the stability of Pluto's orbit has been maintained over long time scales, thanks to the gravitational influences of other celestial bodies. This stability is an example of the intricacies of celestial mechanics, often referred to as the three-body problem, where the gravitational pull between the Sun, Pluto, and Neptune and other planets plays a crucial role in maintaining a stable orbit. Simulations have shown that the gravitational forces from massive planets like Jupiter help keep Pluto's orbit steady, preventing chaos over long periods of time. Without these stabilizing forces, our solar system would be far more chaotic. Given the complex nature of Pluto's orbit, some astronomers have recently raised concerns about the possibility of a catastrophic collision between Pluto and Neptune. Neil deGrasse Tyson and Michio Kaku, both prominent astrophysicists, have expressed concern that such an impact could have profound consequences for the solar system. If Pluto were to collide with Neptune, the event would release an enormous amount of energy, likely destroying Pluto due to its smaller size and icy composition. The debris from the collision could scatter across the solar system, potentially posing a risk to other planets and their moons. For Neptune, a collision could alter its atmosphere and possibly even its orbit, depending on the nature of the impact. Michio Kaku, a well-known theoretical physicist, adds a unique perspective on the topic, linking his expertise in string theory to our understanding of cosmic phenomena. He suggests that by studying the gravitational interactions and orbital dynamics of bodies like Pluto, we can gain valuable insights into the future of space exploration. This knowledge could not only help us better understand the solar system but also guide future missions to explore distant reaches of space. Ultimately, while the possibility of a Pluto-Neptune collision remains unlikely in the immediate future, studying these celestial mechanics offers vital lessons for understanding the solar system's dynamics and preparing for potential risks. Additionally, the lessons learned from Pluto's unique orbit can aid in exploring other distant objects in our solar system and beyond. Exploring distant realms of planetary science, celestial mechanics, and theoretical physics reveals how deeply interconnected these fields are. The movements and interactions of planets, particularly the gravitational dance between Pluto and Neptune, reflect fundamental principles of physics. If Pluto and Neptune were to collide, it would be a spectacular event in cosmology, offering a unique observational opportunity that could provide insights into string theory. String theory posits that point-like particles in particle physics are replaced by one-dimensional strings, aiming to explain the fundamental forces and matter in the universe. Such a collision could generate extreme energy and gravity conditions, potentially unveiling phenomena predicted by string theory, especially regarding particle behavior under intense conditions. Although the impact on Earth would be negligible due to our distance from the outer solar system, the scientific implications of such an event could be vast, enhancing our understanding of the universe's fundamental nature, as envisioned by string theory and other areas of theoretical physics. Pluto's unusual orbit continues to captivate scientists and enthusiasts alike, offering a glimpse into the complexities of celestial mechanics. Its reclassification as a dwarf planet sparked debates and reshaped our understanding of planetary bodies, but recent discoveries about its orbit have reignited interest in its role within the solar system. Astrophysicists Neil deGrasse Tyson and Michio Kaku have raised concerns about the potential for a collision between Pluto and Neptune, highlighting the complex forces governing our cosmic neighborhood. They emphasize the importance of understanding the gravitational interactions and orbital mechanics at play, especially since Pluto's orbit, marked by its eccentricity and steep inclination, deviates from the nearly circular orbits of nearby planets. Unlike its neighbors, Pluto's orbit is distinct, crossing Neptune's path at certain points during its lengthy orbit around the Sun. The gravitational influence of other planets, particularly Neptune, is crucial in shaping Pluto's orbit and maintaining its stability over time. Despite the unpredictable nature of its orbit, mathematical simulations and theoretical models suggest that Pluto's path remains relatively stable in the broader context of the Sun's gravitational field. Although a collision between Pluto and Neptune is highly improbable in the near future, the gravitational interplay between these two bodies underscores the delicate balance of forces that govern planetary motion. Beyond its scientific significance, studying Pluto provides valuable insights for future space missions. NASA's New Horizons mission, launched in 2006, delivered groundbreaking images and data of Pluto and its moons during its historic flyby in 2015. The mission revealed unexpected details of Pluto's surface, including vast fields of water ice and extensive areas covered in frozen nitrogen, expanding our understanding of the geological processes shaping this distant dwarf planet. The success of New Horizons highlights the technological advancements and collaborative efforts required for deep space exploration. By examining Pluto and its moons, scientists gained valuable information about the diversity of celestial bodies and the environmental conditions present in the outer reaches of the solar system. These discoveries hold implications for future missions to explore other dwarf planets and trans-Neptunian objects, helping us better understand planetary formation and evolution. Furthermore, the debate surrounding Pluto's classification as a dwarf planet has sparked discussions about the criteria used to define celestial bodies in the solar system, reflecting broader questions about scientific taxonomy and the evolving nature of astronomical knowledge. Although Pluto meets several criteria for planetary status, such as orbiting the Sun and having enough mass for self-gravity, its reclassification as a dwarf planet highlights the diversity of celestial bodies beyond the traditional 8 planets. Studying Pluto's orbit expands our understanding of celestial mechanics and planetary dynamics in the outer solar system. By investigating the interactions between Pluto, Neptune, and other bodies, researchers can gain deeper insights into the formation and evolution of planetary systems. These insights are essential for developing theories about the origins of our solar system. Understanding the long-term cycles that shape planetary bodies over billions of years is crucial in comprehending the dynamics of our solar system. Pluto's recent reclassification and the subsequent research into its orbit have provided valuable insights into planetary movement, particularly the evolution of the Kuiper Belt, a region beyond Neptune populated by small icy bodies. Examining Pluto's orbit offers clues about the gravitational interactions that might have influenced the formation of planets in the early stages of our solar system's development. By studying the intricate mechanics of celestial bodies, scientists can also inform future space exploration missions, such as the search for habitable exoplanets. Tracking the movements of distant objects in space can help identify promising targets for exploration and assess the feasibility of reaching other star systems. Though the possibility of a Pluto-Neptune collision is extremely unlikely, it serves as a reminder of the dynamic and unpredictable nature of the universe and the potential for large-scale events. As we continue exploring the outer reaches of the solar system and beyond, studying planetary orbits and celestial mechanics will remain a central focus for astronomers and space agencies alike. Pluto's orbit, which deviates significantly from those of the other planets, offers important lessons about the complexities of planetary movement. Despite its erratic path, Pluto's orbital stability over vast timescales provides critical insights into the balance of forces that govern celestial motion. This ongoing stability suggests that planetary systems, including our own, are not always subject to sudden or unpredictable changes. Over immense periods, even small gravitational interactions can lead to significant stability, preventing dramatic shifts in orbits that would have serious consequences. This concept encourages a reevaluation of how we assess the stability of distant planetary systems, especially those far beyond our own solar system. The continued study of planetary movement is not only about understanding our solar system but also serves as a tool for predicting the behavior of exoplanetary systems that we observe from Earth. Additionally, the gravitational dynamics between Pluto and Neptune provide important lessons in orbital mechanics. It's not just the motion of individual planets that matters, but how they influence each other over time. These interactions between celestial bodies shape the very structure of planetary systems. While Pluto's interactions with Neptune may not be widely discussed, they offer a subtle yet significant example of how distant objects in space can influence each other and potentially alter their orbits over millennia. The scientific community's interest in Pluto extends beyond potential collisions with Neptune. As a dwarf planet located at the edge of our solar system, Pluto provides a valuable window into the formation and development of planetary bodies in the outer regions of our solar system, such as the Kuiper Belt. The Kuiper Belt, a region populated by icy bodies, holds important clues about the early solar system's formation. By studying the distribution and characteristics of these objects, scientists can gain deeper insights into the processes that led to the formation of gas giants and their moons, as well as the smaller icy bodies that populate the outer reaches of the solar system. As such, exploring Pluto offers critical lessons that extend far beyond the dwarf planet itself, helping to refine our models of planetary development both within our own solar system and in distant star systems. The insights gained from studying Pluto's interactions with Neptune could also influence the design of future space missions. Understanding the behavior of distant planets, moons, and other celestial bodies will be essential for planning missions to explore the outer solar system. For example, NASA's New Horizons mission, which flew by Pluto in 2015, provided valuable data that may guide future studies of other icy bodies in the outer solar system. Understanding how objects like Pluto and other trans-Neptunian objects, TNOs, behave could help scientists make better predictions about potential future impacts, risks, and opportunities for exploration.